Okay, guys. So first of all, thank you for inviting me here. Also, thank you for Pino for the nice presentation. I want to share here. Well, first of all, my name is Francesco. I work for Anchormen in Amsterdam. Anchormen is a data science and big data consultancy company. And here I'm looking at looking after different projects, and one that I particularly enjoy is an entity matching tool that I'm developing for the manufacturing industry. This work is ongoing, and I've been working on this for a few months. Apologize in advance because I won't be able to open the box as much as Pino did. First of all, because there is some sensitivity on what I'm doing, sensitivity on the data that come from clients, and also because at the moment I'm actually looking at we are smoothing some problems in the deployment. So there are still a few things that we are focusing on solving. Nevertheless, I want to really share the lesson learned, the tool I'm using, all the tools that I'm going to present. They are all publicly available, and especially we refer to one scientific paper which inspired most of this work. So I'm saying pretty much what I'm saying is that I'm showing everything that I can show, and that the most useful part as well. Also, the data you will see, they are dummy data. They will not come from real manufacturing data, but all the challenges are there. Okay, so after this introduction, I just wanted to introduce what type of data you could see in an enterprise. There are usually 3 types of data at enterprise level. One type is a transactional data, so mainly business event, which can be purchase or maybe also click. They're probably transactional data, although I'm not entirely sure. Analytical data, they are usually data that they are kind of produced from analysis from transactional data. They're usually done to monitor business performances. And those are usually the one that, most of the data science projects and tool focus on. But there is also another pillar, another type of data, which is the master data. And those data usually are available, they are related to key business entities, in particular to operations, okay? And this is where we will focus on most of master data and for the manufacturing industry. So master data management is not new. There are processes, best practices, and tools in places which allow you to make use or to apply the best practices of master data. Usually, master data involve a set of different information. The most important one is about the product or the asset, but there is also a customer related to it. There is a location, because a product can be different location of the same customer, and there is always a supplier from which you buy a product. Master data management essentially involved having a unified and centralized data set of operational data, which the company can use essentially to do things, to optimize processes, such, for example, inventory optimization. So if you have a product here and you have another in another location, you can use one of those instead of buy a new one. And in turn, you can optimize your spending, and also you can keep track of procurement. One of the main challenges of this is that most of the cases, products are duplicates. What does it mean? Duplicates means that the data are duplicates, means that for the same physical entity, you may have different descriptions or different data items. For example, in the case of manufacturing, you usually have product identifiers that allow you to programmatically or algorithmically identify the data that you have, the master data that you have. But some of the data, they come with a challenge. So ideally, most of the data, they have an item description. And here, actually, sorry about the misspelling. I'm just checking out description, not description, sorry. But most of we assume that usually it is the case that the items or product, they always have a textual description. So essentially a sentence which has different text or text mixed with codes about the product. There is typically a brand, but it may be missing. There is usually a code, manufacturing part number. That one is usually the most useful information because you can do some matching between key attributes. And the GTIN is essentially the global trade identifier number, which is complementary or alternative to the manufacturing part number. So if everything goes well, you would have a manufacturing part number. You would just do typically a matching query, and the problem is pretty much solved with a rule-based system. And you can apply also some taxonomy with brand perhaps or category. Problem comes especially in manufacturing industry, because most of the cases, in many cases, you miss this information. So for example, let's say you have a company has a plant A, a plant B, the filter break in the plant A. The only way to know if in this specific scenario, you don't have the code for the manufacturing part number and also the global trade identifier, you don't have it either. So the only way is to look, compare text. So what typically happens is an operator from plant A will call operator from plant B to ask if they have that specific filter. And you may understand how difficult this thing is. And also it will not be part of the master data either, because it cannot be live on its own as a text. So this problem here is known in machine learning or in data matching as entity matching. And you have two levels of this problem. The first one is structured data. So typically when you have codes, or if you're able to extract entities from text. So this is what has been tackled historically or so far. And there exists tools that can deal with the problems with this type of data. And also they do pretty well. So in this case, for example, with this dummy example also taken from a publication, you will see that from data set A, you have a set of names or data about a person. Data set B, you also have the equivalent. They are, however, slightly different, but still, if you're able to extract some information and a bit of some simple rules, you can see that the first entry from dataset A match with the first from dataset B, and the third of dataset A match for the second dataset B. Problem comes when you don't have this data already structured, either because you don't have the codes or the names, or because you don't have a capability to extract all these attributes from the text. In this case, if you only have text, then things becomes a bit challenging. And that's what I want to focus today and show you a bit more or less what I've been working on and what the lesson learned so far. The typical workflow for entity matching goes more or less like this. So you have items, descriptions from a database A and a database B. You usually take this item, you apply some pre-processing. Then from this, because remember your task is to find items that match in the database A and B. You undergo through a pair generation. So you generate all possible pairs of items. Then you classify this item. Then you may find that some items are matches, some are not matches. Either are potential matches based on some threshold. For example, potential matches, there are items that are similar, but not similar enough to make sure they are matches. And an expert typically would review these and also make some iteration in the per classification. So here, no modeling yet. It's just the workflow of how these things are usually done. And then you can see also the challenge here, because even though you have maybe a moderate size data set of 1,000, 10,000 elements, then when you go to generate pairs, these things is quadratic. So the number of comparison is the square of that. Actually, it's less than the square, but let's keep it simple. It's a square of that. So 100,000, 100 million, sorry, of items. And so what is usually done, also because most of these pairs, they will be not match, right? There will be only few matches on this case here. You apply some rules such as taxonomy to get rid of all the obvious non-matches, and then you apply classification only on the most likely pairs. And you apply a model typically to a reduced number of the data set. So this is a typical also philosophy that recommender system use, or any information retrieval system use, in which you have first the information retrieval and then you have the re-ranking. And here it's really no different, it's just the use case is a bit different. In classical machine learning that I've seen and also are available in tools that work on this topic, they use usually classic machine learning technique. For classic, I mean before BERT pretty much, and before semantic search became publicly available. And they mostly deal with the structured data. So that means that either you have already, your data comes already separated with the key within attributes, or you have to extract these attributes from the text using, for example, rules or simple entity recognition. But mostly they are manually written rules in order to decrease the errors. The pair generation usually is also simplified, or more than, well, I wouldn't say simplified, I would say it is mostly rule-based, so based, for example, in taxonomy. So if you have products that come from the same brand, you would just filter by brand. If you have the category, even better, you apply a category that specific brand. So you reduce the pair and you're 100% sure pretty much that those pairs are relevant. Then you apply some feature engineering, meaning you take some feature from the text such that you develop some indicators, some signals, let's say, based on the similarity, and you apply some a classifier. You train a pair classifier, which is typically a random forest or a tree-based system. The main limitation with this system here is the extracting the attributes. So this is usually done with the rules. So if you have new data, new rules that you have to write in order to extract the identifier from the text. So what has been, what I've seen recently in the literature of this, and also some other smart guy started this project here at Anchormen before me. It's an application of the latest technologies, so in NLP, especially transformers-based network to solve this problem. And the work is mostly inspired by the paper I'm citing there. Actually, it's a very applied paper. It comes from some smart researcher that have done this tool in a company. So it's quite applied and it's very nice. In this case, the process is quite similar as before, but it would deal with text, okay? So you don't have any more table that's already separated in attributes, but you have list of sentences. The pre-processing is still there, but is very minimal because you just clean the text. And then the pair generation is done differently. So in this case, one of the latest or the state of art for what I've seen so far is converting the sentences into semantic embeddings, specifically using Sentence-BERT, which is the state of art of semantic embedding. State-of-art modeling semantic embedding. You use BERT in a clever way, which I'm going to show you in the next slide. Once you have the semantic embedding, you can do semantic search. This doesn't reduce the problem of generating millions and millions of pairs, but I will show you also later how this can be improved. But also here, eventually you have the most likely pair you want to classify. And the classification is done with plain BERT. So no fancy model, just BERT as a sentence pair classification as one of the main tasks that you can use. And one of the reasons I particularly like this is that if you are lucky enough to have commonly available, common sense, let's say, descriptions, all these models here, Sentence-BERT and BERT, they come pre-trained for different fields and also in different languages. So what I'm trying to say that if you're lucky enough to do something quite generic and not in the manufacturer, unfortunately, because those are very language specific, then you may produce high quality pairs. To classify high quality pairs is a zero shot. So without any labels, any labels, any pair labeled. In our case, we use labels, and I'm also fine-tuning both BERT and the Sentence-BERT, and I will mention this a bit later on. As I mentioned, it's quite nice that BERT come with the sentence-PERT classification as one of the tasks it solves. That you can is ready to be used to solve this task. And essentially here, what it boils down is to feed the sentences of description of item 1 and item 2 to a BERT architecture and use as a target label the class. In this case, the class is 0, 1, 0 if it's not match, 1 is if it's match. And one of the challenges is if you have to fine tune it, not for fine tuning because it's pretty clear how to do it. The challenge is to prepare the pairs, specifically the the negative pair and the positive pairs, but it is the script on the paper. It's just a bit of coding and a lot of experimenting. I don't think it's the most efficient thing, actually. The most efficient thing in terms of pair mining comes from Sentence-BERT, which has essentially used BERT, but in a Siamese architecture in which you have BERT in one tower will have a BERT model, the other tower will have another BERT model. And in this case, you don't feed both the sentences like this all together to do sentence-BERT classification, but you just care about the embeddings and you optimize for similarity. It turned out that in the last few years, there's been a lot of research in the similarity losses. And the nice thing is that Sentence-BERT have all of them. The difference from preparing pairs here and in this case here is that the pair are prepared and mined already in the similarity loss in between the batch when it trains. So it's quite efficient, it's quite nice, and it saves you a lot of coding. How is this used? So this is used for semantic search. So if the model is properly trained, in this case, you may need to fine tune it, like in my specific case. Two pairs that happen to be similar in reality, or ideally happen to be sentences or description of the same real physical item. They will be close in the semantic search space, okay, in the embedding space. Sorry. And in that case, you can find with semantic search, you can find the most highest quality pairs for each item and feed those to the final classifier. Problem is that even though you have produced high quality pairs, and perhaps also this pair, these embeddings, they are, for example, 700 vector 700 item long, you still have many of them, right? So even if you have 1 million item in which you are searching matches or duplicates, then you still have to do 1 trillion of comparisons. And even if you have a quite large, a quite fast routine that will take you 0.01 millisecond, it will still take you 116 days to do something like this using brute force search. Thankfully, a lot of research has been done like this. Thankfully, these techniques, they are also relevant for recommender systems. And one of the, nowadays, the recommender systems are very popular. A lot of people are working on that, including also Google. And a lot of innovation has been done in approximate search. So in this case, you don't do any more. So in the brute force search, in order to find the best pair for item 1, you will need to look through all the existing pairs, all the existing items. So in this case, if you have to go through all the 1 million item and do this 1 million times. If instead you use approximate nearest neighbor algorithm, this is a way more efficient way to do this problem, because you already develop, you essentially build an index which allow you to partition the space, more or less like in the image that I'm showing on the right. And in this case, essentially, you only search on this partition here. I see something in the chat. Okay, sorry. So there was a question. Coming to the end, I just wanted to show you some practical challenges that I'm facing. Few of them I've solved, especially the first. The last are still a work in progress. Few I haven't even started yet. One of the first challenges is obviously the pairs. The pairs are needed for fine-tuning. The model will work also without pairs, but not with going to best accuracy. We'll need to label pairs, and especially to find an expert that label these pairs for you. Ideally, they would be sort of, this expert would be included in the loop so that you can do some active learning, but to start with, you need someone to label the pairs or to have some other smart system. Fine-tune BERT for sentence-BERT classification is not that difficult. As I mentioned, the most difficult part is to mine positive and negative BERT correctly. Fine-tune sentence-BERT for semantic embeddings, that's more challenging, just because there are a lot of options there, a lot of loss function, a lot of way to evaluate, because it can solve several tasks in order to find the one that work better for best for your problem. You need to experiment a bit. Classified description in different languages is very relevant for this problem, because, for example, a company may have a plant in one country and another plant in another country. You would like also this to work. It's possible, just extra complexity and the fine-tuning. The approximate search may need to be tuned as well. For now, I'm using with the default, but for the best recall, you probably need to experiment that a bit as well. Putting together these into a pipeline that actually work end-to-end is what I'm focusing at the moment with the help of colleagues. There's very smart colleagues here, and but it's not obviously trivial. And finally, one of the things that we would like to do, and because all these things work on GPU, sometimes you struggle with this, is to have a system deployed with sufficiently low latency. And these kind of latency issues may come both from the search that I mentioned, but just also to do inference using BERT and sentence-BERT may take time as well. So this is something we are experimenting and tried at the moment. And with this, I would like to thank you for your attention. And please, if there are any questions, just let me know.